Welcome to Ask and Learn.
Here we have the law of laminar flow, and we're going to use it to look at the flow of blood through a blood vessel. And for this problem, we're given some specific numbers to plug in for the constants. So we're going to plug in 3,000 for the pressure, and the value of eta, which is that one that looks kind of like an N, it's a Greek letter, or maybe it's pronounced eta. The value of eta is given as 0.027. The length is given as 3. The radius of the blood vessel is given as 0.01. Okay, so now that we have that, we could go ahead and take a step to simplify it. The fraction in the front we could simplify a little bit to 250 over 0.027. And if we want to, we can simplify the number inside the parentheses as well. Not going to make a whole lot of difference. Okay, so for part A, what we're going to do is find the velocity of the blood at various points in the blood vessel. At r equals 0, which would be smack dab in the middle, not close to the walls at all, but right through the middle. And that's going to be, you're going to plug that in your calculator, and that's going to be approximately 0.925. And then we're going to find the velocity of the blood when it is about 0.005 centimeters from the middle, and that would be approximately 0.694. And then we're going to find the velocity when the blood is right there at the edge of the blood vessel at 0.01 units from the center, and that would be 0. So that doesn't sound good. That means the blood is not flowing at that part. And we can see that the velocity of the blood is decreasing as we go closer to the edge of the blood vessel. Okay, for part B, what we're going to do is find the derivative, and that is known as the velocity gradient. And then we'll evaluate the derivative for those same three values of r, and that'll tell us how fast the blood is flowing, or actually the rate of change of the speed of the blood, because we already have the speed, the rate of change of the speed. Okay, so the derivative of this, we can leave the constant there, and we'll multiply by the derivative of the inside function, and that's going to be negative 2r. And we could simplify this if we want to. This is negative 500 r over 0.027. So then we're going to go ahead and substitute the various values of r in there, starting with r equals 0. And we end up with 0, which means that the rate of change of the velocity is 0. There's no change in how fast the blood is flowing at that point. And then v prime of 0.05 is negative 92.59 approximately, and v prime of, this is v prime of r, by the way, not t. There's no time involved in this. We'll change that to an r. V prime of 0.01 right there at the edge of the blood vessel is about negative 185.185. So what that's telling us is that the most change is happening at the edge, because that's the greatest velocity, greatest rate of change of velocity. We also saw and discussed earlier from part A that the blood is flowing at the greatest speed in the center.